Hi, everybody. Welcome to our next idea in grade 12 U Prep Physics. What we want to talk about today is another sort of change to the ideas you learned about in grade 11 U Physics. Um, so if you remember, we've been talking about potential energy about gravity and fields. And we want to again examine our now expression for gravitational potential energy. So the one that you probably recognize from grade 11, this guy right here, that this is the work required to lift an object up a distance h, or the change in an object's potential energy when I lift it some distance above the surface of the Earth. Now, just briefly here, one thing to keep in mind when you derive this expression in grade 11, that you considered the force of gravity to be a constant, given by the F, force of gravity is equal to mg. And you remember that that force, as we talked about last time, is only valid if we're near Earth's surface. So as soon as we have this force changing, which means g is changing, we're traveling large distances, things like that, that this expression is no longer valid. So our goal today is to try and get another expression for potential energy, and see if we can get something a little more general, so it's not tied just to the surface of the Earth. And the way we're going to tackle that is by our other definition of change in energy, that work is a process that transfers energy. And so whenever work happens, there is energy being transferred. And we want to talk today about doing work against gravity. Uh, I guess I should add that here. So under a force of gravity graph. So anyways, we want to look at how much work it takes to fight gravity and how much energy is sort of stored as you're moving two objects further and further apart from each other. And so what we can do is we can look at this sort of graph here. This is the force versus separation graph. So this would be the force pulling two objects together, and R would be, again, the separation between them. And we looked at this sort of shape last time. But if you remember that our other sort of idea for work is that instead of just multiplying force times distance, we can actually do it as the area under a force distance graph. And so what we're looking for here is this area that I'm kind of highlighting. And so this is the area that we want to find in order to get the work. And this area will represent the work done by whatever's doing this to move an object from R1 to R2. So you can see it's an amount of work, so that means we're gaining some potential energy here. But the problem is, if you look, is that that's a very funny looking shape. I mean, it's almost a triangle, but not quite. It's sort of circular, but again, not quite. And so it's difficult to actually get the area underneath. So if you actually want to understand exactly where it comes from, unfortunately, again, you need calculus, which even if you're in calculus this semester, it's a little beyond where you're going to be going in high school. But really, all we can do is we can recognize that the area is going to be given by this expression. And it looks kind of strange, but you recognize R2 minus R1 is the base of this shape, and the square root of F1, F2 is another way to sort of average out the forces. So instead of adding and dividing by 2, you can multiply and take the square root. I believe it's called the geometric average as opposed to the arithmetic average. But it's just another way to find sort of the average force and say, well, it's kind of like this area here, and then anything up here will be replaced by anything here. Of course, I'm oversimplifying it a little bit, but hopefully you can trust me a little bit, and we can recognize this is the expression for the area of this shape. And so now all we have to do is go through and plug in values we know. So we know, again, the force is given by this expression we talked about last time. Do a little bit of rearranging and multiplying, and we end up with the area is given by this expression here. And if you notice, this is very, very close to final minus initial. And we want to kind of get in that form of final minus initial, because then we can talk about the change in something. And again, I think you can probably follow along that change in that something is going to be the gravitational potential energy. So what we're going to do is I'm going to write this as just flip these terms around. And if I do that, I'm going to have the change in potential energy is given by this expression here, but again, I'm going to change them around so they have the R2 minus R1, and I end up with this pretty simple looking expression here. But I think you can also appreciate that as R goes to infinity, as R gets bigger and bigger and bigger, we're actually going to have less and less force. So if we do that sort of idea, let R go to infinity, we're going to come up with an expression, and this will be our expression for gravitational potential energy. So this is our new expression for gravitational potential energy. So it's going to be G mm over R. Notice the minus sign here. We'll talk about that in just a second. Um, and this looks kind of similar to the force. And there are some parallels because remember the force of gravity was given by mg. Oh, the one that's terribly written. I'll write that again. F equals mg if we're near the surface of the Earth, and the potential energy if we're near the surface of the Earth is mg h. And so this is very similar to the force expression, just with one less distance power in there. And so it's like we're doing this again. We're multiplying by some distance measurement. And so then there's our in general expression for potential energy. Just before we move on, to point out that the R we're talking about here is the distance between the center of the objects. So we're not talking about surface to surface, it's center to center. And that this expression we derive for potential energy is actually valid for just about any substance, or sorry, any system. The only constraint is we have to be outside both objects. So for instance, this wouldn't work if we tunneled inside of the Earth and measured the potential energy of our tunneling robot. So we have to be outside of both objects. So satellite orbiting Earth, you standing on top of the planet, the moon orbiting the Earth, the sun going around the center of the galaxy. So all of these would be fantastic ways to look at this. All right, so let's take a look a little more at this expression. Again, copied right here. What the heck is going on here? And let's first of all look at this graph. So this graph again graphs the potential energy, gravitational potential energy, as a function of R, and again, R being the separation. And so if you notice that it's, first of all, it's always negative. And that's something that some people find a little, that we always have negative energy. And that's, again, it's a bit uncomfortable for some people. But remember, all our potential energy is kind of measured to some sort of reference point. And so what we're going to be using for a reference point for this sort of general expression is infinity. And what I mean by that is that we're going to talk about how much energy something would lose, how much potential energy something would lose if an object came in from infinitely far away. So they're so far away that the force of gravity is completely negligible between the two of them. And we're talking about letting that thing fall, how much energy would potential energy would it lose? Or if I let these two objects freely fall towards each other, how much kinetic energy would these objects have? And so again, if I have something over here at, they're so far separated that it's infinite potential, or sorry, infinite distance, so zero force, and we're going to call that zero potential energy. As it's becoming closer, it's losing potential energy, which again makes sense with your common sense, that when things come closer together, it should be losing potential energy. Now, the only difference here is we're always negative. But notice that again, it's okay because we're still talking about generally the changes in these things' potential energy. But if we use this idea here, we can actually do something that's more powerful. Not only does it represent the energy these things would have lost, something else we'll talk more about next time, but it represents the amount of energy you actually have to put in to separate these objects. So let's imagine you wanted to throw a rock away from the Earth and throw it so hard it never came back. How fast would you have to throw it? And this would give you an idea of the energy you would have to use to do that. So if you're down here, you'd have to get it all the way to go up this full distance and end up with a zero potential energy. So I hope that makes some sense. And what we'll do now, of course, is look at some examples. So we'll start with one that we've done, well, not exactly, but very similar in grade 11 university prep. So we have a person standing on the surface of the Earth. If we were in grade 11, we'd probably say that this person had zero potential energy because we're often using the ground as our reference point. And we said we're never going to have this person leave the surface of the Earth, so we don't have to worry about the fact that the force of gravity can change. But now we're going to pretend that we're going to actually then look at this thing in general, remove all those constraints about forces being constant and person never leaving the Earth. And we want to know how much gravitational potential energy is stored in the Earth person system. Let me just talk a second about this idea of Earth-person system. So again, in grade 11, we probably talked about how if a person's standing on top of a ladder, that person has potential energy. But an equally valid way to talk about that is that the Earth itself has potential energy. And we can looking at the force that the person's applying on the Earth. and they come with the exact same number. So instead of doing that, especially considering that in this year we're going to be talking about things that are nearly equal or exactly equal in magnitude of their masses, we're going to refine that idea and talk about the system. So even though the person is normally what we consider the object and the Earth is what's causing the gravitational field, we could actually think of the reverse. So we're going to call this the Earth person system. Um, Earth person not meaning like Earthling, it means like Earth/person system. So if we wanted to know the gravitational potential energy stored in this system, I hope again you can see that we're going to have to look at how far apart are the centers of these people, and we're going to need to know the masses. As I mentioned to somebody in class the other day, that you don't actually have to memorize any constants in terms of masses of Earth or capital G or the radius of the Earth, but here they are right here. They're in your textbook. They're on the internet. You can find them all over the place. But the mass of the Earth, the radius of the Earth, and this gravitational constant G. And we have the mass of the person, which is 64.5 kilograms. So if we just take our expression for potential energy, we put this into this expression here for our gravitational potential energy, and we end up with this value here of negative 4.03 by 10 to the 9 joules. So again, a couple things to point out here. One, this is negative, and again, that makes sense because they are closer than infinity, then they've actually lost potential energy if we brought the person in from infinity. So we have a negative potential energy. And the other thing to keep in mind is that look at the size of this energy. It's 10 to the power of 9. And again, it's an incredibly large amount of energy, but it makes sense considering what it represents, which actually brings us to B. What does this energy represent? And what it actually represents here, this is the energy stored in the system. So the two ways we can think about it, if this person were to fall towards the Earth from so far away we consider it infinity, traveling from way up here, look at my awesome drawings, of course not to scale, but as this person falls from infinity, by the time they get to the Earth, they would have this much potential energy, 4.03 by 10 to the power of 9. They would have lost, this much potential energy, 4.03 times 10 to the power of 9 joules, and they would have gained this much kinetic energy. So this person would be traveling incredibly fast. The other way to think about this, in order to leave the Earth, so if we wanted to give this person, fling them on a slingshot out of the Earth, they'd have to have this much energy. And if they had this much energy or more, they would never, ever come back to the Earth. They would have enough energy, they would escape Earth's gravitational field, and they would be gone. Anything less than this, and eventually they would fall back to the ground. Right, so again, I hope that makes sense. Let's do one more here. And this time, let's remove ourselves from the Earth entirely. Let's take a look at asteroids. So we have two objects, the only two objects in the universe, two asteroids. Now again, we can say this is ridiculous. Of course, there's more than two objects in the universe. But as long as we're far away from all sorts of other things, this is actually a pretty good approximation. And so let's say again, we have these two asteroids. They're both 5,000 kilograms, and they're 300 meters apart. I want to know how much GPE is stored in this system and how much energy would be needed to be added to this system to triple the separation of the asteroids. So let's start with A, how much GPE is stored in the two asteroid system. So again, hopefully you can see that we're just going to be looking at this expression here. And G, of course, we know capital G. What are we going to use for R, do you think? Well, for R, it's just their separation of 300 meters. And we have to worry about the two masses. Now, which one's big M, which one's little m? It made sense, or it was quite straightforward before because we used Earth and person, but now we have asteroid 1 and asteroid 2. Or is it asteroid 2 and asteroid 1? Well, again, hopefully you can realize that it doesn't make it like a difference which one we pick because it's multiplicative, and so you can actually do those in any order you wish. So 5,000 times 5,000 or 5,000 times 5,000. Again, something else to remember is that there is no preferred sort of object as the one doing the attracting, since they're both equally attracting each other. So we're going to put those numbers in as I've done here. So 6.67 times 5,000, 5,000 divided by 300. And we do that and we get negative 5.56 by 10 to the minus 6 joules. Now this number again is incredibly small, 10 to the minus 6 joules. But again, this is something I think is kind of neat, that these asteroids, 5,000 kilograms, so these would be pretty massive things by people standards, and they're only 300 meters apart. but they're only storing this much energy. So there's not a lot of potential energy stored in these things. And again, it goes back to the idea that gravity is a weak force compared to the other ones, which again, we'll talk a little bit about later on in this course. All right, so there's the potential energy stored and how much energy we needed to add it to this system to triple the separation of these asteroids. So asteroid 1, asteroid 2, this was 300. Now I want to separate them, say here and here. So this distance is now 900. And I want to know how much energy would I need to add to this system. Sorry, 900. How much energy would I need to add to this system to do this? And so let's go through how we figured out. Well, we knew the energy that was stored at 300 meters separated. So let's figure out how much energy it has when they're 900 meters separated. And so we'll do the exact same thing, but now we're going to have a different separation. It's 900 meters. And so this is how much energy is stored in the system now. And so you might think, great, great, we're done. There's the energy it takes. But no, this is the energy stored in this scenario, the 900-meter separation. We still have to look at how much more do I have to do. And so we're really looking for the change in this thing's energy. How much energy changes are going on? And so we're going to be looking at this. So it's going to be EG2 minus EG. And you plug in our numbers, and you get this. A couple things again to point out that first of all, we have a positive number, which means we have to add energy to this system. And again, that should hopefully fit with your idea of how energy works. We're adding energy to this system because we have to pull these things further apart. We have to push to bring them apart. And the other thing to point out again is just how freaking small this is, that we can rip apart these asteroids by 600 meters, and it needs a minuscule amount of energy, -6 joules. So this is less than you'd get from eating, like, I don't know, one chocolate chip. So you could actually move these asteroids quite easily in terms of the energy you'd have to add. Now, if you want to do it quickly, if you'd have to have a little more power than that. But if we just want to separate them, we don't care how long it takes. It doesn't take much energy at all. All right, so I think that's it to me in terms of explanations.